Lastly, let's consider a Rankine cycle with superheat and reheat. State 1 is the inlet of our pump, and state 2 is the exit of our pump. From state 2 to 3, we are adding heat into our system. From 3 to 4, we expand through our high-pressure turbine. And from 4 to 5, we additionally reheat our working fluid to a higher temperature under a constant pressure process. So from state 4 to state 5 is an additional heat input process. Then from 5 to 6, we have work of our low-pressure turbine. And then from state 6 to 1, we reject heat, as has done previously. To analyze this system, let's assume that steam enters our high-pressure turbine at 8 MPa and 480 degrees centigrade. It then expands to 700 kPa. It is then reheated under a constant pressure process to 440 degrees centigrade before entering our low-pressure turbine, where it expands to 8 kPa. Saturated liquid exits our condenser at 8 kPa. If our net power produced is 100 megawatts, we want to determine our thermal efficiency, our backwork ratio, the mass flow rate of the steam, the rate at which heat is supplied, and the rate at which heat is rejected from the cycle. To begin, we recognize the enthalpy and entropy values at state 1, 2, and 3 are the same. State 3 is the inlet to our high-pressure turbine at 8 MPa and 480 degrees centigrade. That means we have to find states 4, 5, and 6 in terms of their enthalpy values. At state 4, we exit our high-pressure turbine at a pressure of 700 kPa. At state 5, we enter our low-pressure turbine at a pressure of 700 kPa and a temperature of 440 degrees centigrade. Then at state 6, we are rejected to a condenser at a pressure of 8 kPa. We're going to assume the entropy between state 3 and 4 is the same, and between 5 and 6 is the same. For us to determine our enthalpy at state 4, we are going to relate our enthalpy and entropy via quality. That is, our enthalpy at state 4 would be S4 minus SF per SG minus SF times the quantity HG minus HF plus HF. Our enthalpy at state 4 is found to be 2,740.86 kilojoule per kg. State 5 is going to exist as a superheated vapor with a temperature of 440 degrees centigrade and pressure of 700 kPa. We will find our enthalpy and entropy via interpolation between our 400 and 500 degrees C temperature entries and our 600 and 800 kPa pressure entries. In doing such, we can find that our enthalpy at state 5 is 3,353.866 kilojoule per kg, and our entropy at state 5 is 7.75763 kilojoule per kg. As done in examples 1 and 2, we're going to use quality to relate our entropy and enthalpy values at state 6. Our enthalpy at state 6 can be found as our entropy at state 6, which is the same as our entropy at state 5, minus S of F per S sub G minus S of F times the quantity Hg minus Hf plus Hf. Thus, our enthalpy at state 6 can be found as 2,427.687 kilojoule per kg. Now that we have our enthalpy values, our efficiency is calculated as the work of our high-pressure turbine, which is H3 less H4, plus the work of our low-pressure turbine, which is H5 minus H6, minus our pump work, which is H2 less H1, per our heat input. Our heat input occurs under two different processes, reflected as H3 less H2, and we also add heat under a 700 kPa constant pressure process, which is reflective of H5 plus H4. Thus, we need to calculate each of these respective quantities. H3 plus H4 is our high-pressure turbine work, which is 606.868 kilojoule per kg. H5 plus H6 is our low-pressure turbine work, which is 926.179 kilojoule per kg. H2 plus H1 is our pump work, which is 8.059 kilojoule per kg. H3 plus H2 is our first heat addition process under our 8 MPa constant pressure process, which is 3,166.321 kilojoule per kg. And H5 plus H4 is our heat addition process under our 700 kPa constant pressure process, which is 613.006 kilojoule per kg. Thus, our thermal efficiency is 40.35%, which is higher than a cycle that just has a superheat. The backwork ratio is our pump work per turbines, and we have to include our low pressure turbine within. So our backwork ratio is H2 less H1, which is our pump work, per H3 less H4, which is the work of our high pressure turbine, plus H5 less H6, which is the work of our low pressure turbine. Substituting in our values, we have our backwork ratio is 5.26 e to minus 3, which is less than that of what we determined solely having superheat. Our mass flow rate of the steam can be determined via our net work out, which includes our high pressure and low pressure turbine work. Thus, m dot times H3 less H4 plus H5 less H6 minus H2 less H1 should be equal to 100 megawatts. Or solving for the mass flow rate of the steam within our system, we get a value of 65.57 kilograms per second, which is less than our superheated cycle. The heat input has to consider both heat addition processes, i.e. H3 less H2 and H5 less H4. Our heat input into the system, after we substitute in our value for mass flow rate and enthalpies, is 247.81 megawatts, also less than what our superheat cycle required. Lastly, our heat rejected from our condenser is one and the same. H6 is now updated for having a higher quality, but our mass flow rate has decreased, and we find our heat rejected is 147.82 megawatts. Once again, a lesser value than just a superheat Rankine cycle.